Welcome. I am Professor DebRoy and I am from the Material Science and Engineering Department of Penn State. I am speaking with you from the University Park campus and I hope that all of you are doing well. I wish I could be with you in a room, but I am confident that you will all do just fine online. I want to start with a quotation from the founder of Intel, Gordon Moore. Could you please take a moment to read the quotation on your screen? See, the quotation emphasizes the importance of fundamentals, right? You will see how important the fundamentals are, and you will also experience how we actually use these fundamentals in understanding many important processes and properties. So a little bit about what I do that may be of interest to you. In my spare time, I edit a journal that I founded about 25 years ago, and this is the highest impact factor journal in welding and joining. I volunteer my time to various professional societies, and one of them that may be of interest to you is that I work with the Research and Development Committee of American Welding Society that awards scholarships and assistantships to graduate students. I organize conferences and I have done so for many conferences, and I work with a lot of companies as a consultant. So I've also taught in universities in many countries. I'm also a Fulbrighter. You know that the Department of State awards American citizens to go in different countries as their ambassadors in cultural and educational affairs. So I held one of those distinguished chairs in the Federal University in Brazil. I want to also mention that I was always fascinated by the way the important everyday engineering materials are made and improved. They're improved mostly behind the scenes. So most people don't know how these materials that we now take for granted actually are made and improved. So I have been thinking about this issue for a long time, and together with my colleague Sir Harry Badesia in Cambridge University, we just published a book about how these engineering materials that we use every day come into being. So what are the most important accomplishments of engineers in the last century? Well, according to the National Academy of Engineering, here are 20 very important accomplishments in the last century. So please take a moment to review this list and see which of these great engineering achievements required important engineering materials. Okay. Now, this list includes almost all of the important things we can think of, like agriculture, supply of clean water, energy, transportation, education, healthcare, anything that is important to us. They're all here, right? And more. And so, which materials allow us to make all of these? I think you will be surprised. Most of the important engineering materials consist of metallic materials and to a much lesser extent other materials. How do we know that? Review the annual production values of important engineering materials. If you take just one variety of steel, and look at the dollar values of the raw carbon steel that we produce, it's $195 billion. Remember, this is before we make any component out of this hunk of steel. It's the material that is simply coming out from the steel plant. We haven't made anything out of it. When we make products, the dollar value goes up by at least a factor of 10 to 100. So instead of 195 billion, it will be 1,950 billion and above, right? Okay. If you compare the dollar value of the production of carbon steel with worldwide ceramic sales, it's very difficult to even plot this number in the same scale. And we have a break in this scale. Remember, 20, 40, 60, and then it jumps to 175 because everything else is below $60 billion. Worldwide semiconductor sales, about 24 billion, little less than 24 billion. Aluminum, way below that of steel. So where are these used? In housing, in transportation, in agriculture, in machine tools and machinery, and all manufactured goods. All of them would need metallic materials. That's another very important thing to keep in mind. And also, metals producers are major employers of our graduate, starting from steel companies near Pittsburgh. There are all kinds of companies. If you look at their SIC code or SIC code simply means that if you are a registered company in the state of Pennsylvania, you declare your primary business interest. And the primary business interest in most of the companies that do business in Pennsylvania are metals. They deal with metallic materials, and they are the major employers of our graduates. Processing is also changing, right? There are new processes in manufacturing. Even steel is processed in a more sustainable way today than we did 50 years ago. So there are many examples one can provide as to where we are advancing the processing technology. Take, for example, the International Space Station, okay? And this is the commander of the International Space Station, and they needed a range because their range failed. So what they did was they told NASA that we need a range, but there was no resupply mission planned in the near future. So what NASA did, that instead of physically sending a range, they actually sent a computer program for 3D printing. And they had a desktop printer inside the space station, so they could actually physically print this range right inside the space station. So you see, the manufacturing is also changing. Okay, it is remotely made from Earth, and the product is coming out from a desktop 3D printer inside the space station. General Electric has a plant in Alabama that makes components of jet engine. And what they are printing, they are also 3D printing components like this particular fuel nozzle. This particular nozzle used to be made using some 20 separate components. Now, thanks to the new 3D printing or additive manufacturing, they can print this component all in one piece. We could not even think of that 50 years ago. And more important, the knowledge of materials is more critical today than any time in our history. I'll give you one example. Look at this ship. This ship was built around the Second World War, so more than 60 years ago. We built about 3,000 of these. But what we found was that many of the ships had the same fate as this particular one. This is not a combat situation. This is simply in the port, okay? And it's breaking open into two pieces. So why is that? Of course, it's because of the wrong type of material, right? So wrong choice of material, but what is the material? Well, of course, it is steel. But what type of steel? We have to then know how we actually design and designate a particular category of steel, right? That's what we need to know. So let's look at some of the standard designations of steels. So these are some of the tensile strengths of rolled and heated, slowly normalized, we call it, steel. So look at the range of strength from about 61 KSI to more than twice that much, very close to 150 KSI. And what's the difference? What's the difference? Well, we are designating each variety of steel by these four numbers. The first two, like here, 10 always, designate the amount of alloying elements. And the last two give us the concentration of carbon. So these are all carbon steel. So let's take 1030 steel. This 10 is the extent of alloying, and this 30 is the concentration of carbon in the steel. So let's look at what that means. XXYY. XX is the alloying element content, YY is the carbon content. So 1030 steel, 10 means no alloying element, and 30 means 0.30% carbon. So 1030 means a plain carbon steel containing 0.3 weight% carbon. That's what it means. So 1040 similarly would be a plain carbon steel containing 0.4 weight% carbon. So carbon content can change the strength of the steel, but so can what we call heat treatment. That means if we rapidly cool it, we call it quenching, and we heat it, we call it tempering, gives you a different strength. Similarly, if you add a lot of alloying elements, like in this case, 8640 has 0.5 chromium, 0.5 nickel, and 0.2 molybdenum, containing 0.4% carbon, so 40 means 0.4% carbon, and 86 means nickel, chromium, molybdenum containing steel of this concentration. And that gives you the strength, which is double the 1040 strength. So what we are looking at is that the carbon content has a great deal to do with the strength, and the alloy content also affects the strength. And so does the heating and cooling, we call heat treatment. So what is it we are saying? If we change carbon content, we can expect a change in strength. If we add alloying elements like we did for 8640 steel, 86 means 0.5% nickel, 0.5% chromium, and 0.2% molybdenum. And then that also gives more strength. We can heat and cool and we will talk a lot about the heat treatment, how to change strength and properties using heat treatment. It changes strength. So there are many ways metallurgists can change the strength of a material. Okay, mechanical work is one of them. You hammer something, you make it harder, right? And you change the strength of that. So the question is why? Why is this strength changing? Well, what has changed? Changing carbon content, changing alloy content, heat treating, or working on it mechanically, all of them will change what we call microstructure, in short, structure. So structure changes properties. If we change structure, we will change the properties. That's another important thing that we do in metals processing. Okay, changing structure changes properties. Let's take one other example. A sports car, right? Acura. Acura NSX is a all aluminum sports car. 3-liter engine, 270 horsepower. Okay, so this is nothing to sneeze at. Top speed 170 miles per hour, and this is less than 3,000 pounds. Okay, ton and a half. 0 to 60 mile, well, 5.7 seconds is not probably the best, but it's nothing to sneeze at. 23 miles per gallon, and it will set us back by about 55-60 K. So let's think of what it contains. All aluminum car consists of a body, which is aluminum, engine head, which is aluminum, intake manifold, seat frames, steering arms, chassis, brake calipers, and transmission housing are all aluminum. But most surprising of all, suspension arms on which the whole car sits on, the suspension arms are made of aluminum alloy. Normally, aluminum we consider to be a soft metal, right? So can the suspension arms be built with aluminum alloys? Well, you will be surprised. Suspension arms have to be pretty strong, and aluminum we would call very soft. But if you add about 4.4% copper to aluminum and heat treat it, its strength can be dramatically increased. Okay, how much? 13 ksi for pure aluminum, and aluminum 4.4% copper can give you 5 times that much. 69 ksi, unbelievable, right? And all of it, all of this huge change is because we added 4.4% copper. So look at the fantastic improvement in properties by adding a small amount of alloying element. So in Acura NSX, how do we know that this would be so strong? We use a metallurgical roadmap called phase diagrams, in which we plot temperature versus composition, and it can give you a wealth of information for the engineers. It can also tell us how heat treatment can affect structure and therefore properties. So before we finish, I want to give you a grand challenge. This is indeed a grand challenge to all engineers of our time. This is something that has not been built, but we are thinking about it. It's called a space elevator. Have you heard of it? So on Earth, we have a ground station. And in this space, we have a geosynchronous satellite, What is a geosynchronous satellite? It's a satellite whose position with respect to the Earth does not change as the Earth rotates. Okay? And we connect the geosynchronous satellite to the Earth station using a long cable. And then we have a counterweight so that the wire doesn't wobble. Okay? So this is a very special cable. And a space elevator is a long cable extending from our Earth's surface into the space to a geostationary Earth orbit, which is this particular satellite. Okay. So what you can do, you can run an elevator on this cable, hop into the elevator and hit the button for the 11,457,600th floor and hop out. And when you do, you will be right into the space. No other machinery necessary. You don't need a rocket. You simply get into an elevator and press a button and you will be in space. That is what we are trying to construct. And in fact, NASA Marshall has already got the plans. It's not feasible today, but it will be towards the end of this century. Who will build it? You will build it. All of you will help. And the concept was there in a science fiction book written by Arthur Clarke, a British-born science fiction writer who lived in Ceylon, a small island south of India, for all his adult life. And he wrote a book called The Fountains of Paradise. And in The Fountains of Paradise, he actually described this particular space elevator project. But NASA has since adopted it with all seriousness. There is a person who is manager of space elevator project, paid from everybody's tax money. So it is NASA's job to construct it before the end of this century. So we'll get rid of all our rocket engines and big fuel tanks and all the other gadgets, and instead we'll have a space elevator. All right. So what's the critical part? Why are we not building it today? Why do we need to wait until the end of the century? So we need materials that can actually bear the weight of a very long cable. And what type of material can we make it of? What would be a suitable material for space elevator? Well, many people think of carbon nanotube. Have you heard of it? A carbon nanotube is like this. If you have a sheet of atoms, all these round balls are carbon atoms, and you roll it up and you make a very tiny, teeny tube. That's a carbon nanotube. And if the carbon nanotube is very small, let's say about 460 nanometer, it has a strength of about 150 gigapascal. But if you now go from nanometer to micrometer, you increase the size of this nanotube little longer and up to about 1.8 micrometer. Micro is 10 to the power minus 6. So 1.8 into 10 to the power minus 6 meter as opposed to 460 into 10 to the power minus 9 meter. The strength drops precipitously from 150 gigapascal to only about 24 gigapascal. Why does the strength drop? It's because in a larger specimen, there are always flaws, right? This is looking very nice on a diagram, but in practice, some of the atoms would be no show. they will be missing from their designated location. So that will be a defect, a vacancy, if you will. So all these defects reduce the properties. And the larger the carbon nanotube, the lower the property. For example, if we make a carbon nanotube that is 2 millimeters in length, the property will drop from about 150 gigapascal to about 1.7 gigapascal. So you can see that if we try to make a cable for the space elevator, the properties would not be anything close to the property of a very tiny, small carbon nanotube, because any system that relies on perfection is bound to fail. That's one of the laws of engineering science. So carbon nanotubes may have many exciting applications, but I don't think we are going to use it for space elevator project. So what can we use? Take steel. Take carbon, manganese, silicon, steel of this composition. Okay, 1.5 silicon, 2 manganese, 1 carbon. If you heat it to 950, hold it there to make a particular phase that we call austenite, and then put it in a pizza oven. And yes, you heard it right, a pizza oven that can give us about 200 degrees Celsius for 10 days. So cook it like we cook pizza, but for 10 days. The structure you are going to get is like this. It's a nanocrystalline structure. It has excellent property and, more important, excellent toughness. So it is not just the strength, it's also the ductility. So it doesn't break if you hit it with a hammer, okay? But even this 200 to 2.5 gigapascal is not good enough. So today we don't have the right material for the space elevator. But we are hoping that given many decades, we'll be able to get one. So in summary, what is it we did in today's class? We talked about the course logistics, and we reviewed how important engineering materials are for our standard of living and for our agriculture, distribution of clean water, for housing, for transportation, you name it, we need these engineering materials, particularly structural materials. Many of them are metallic materials. And for those materials, the properties depend on structure. And sometimes large engineering structures fail, and they can be often traced to wrong structures or wrong materials used for the construction of the structure. So that is all today. When we come back next time, we'll be looking at the structure of crystalline solids, because we recognize that structures affect properties. So thank you and stay safe. I will see you very soon. Goodbye.